Here we are in the last section of this unit, and in this section we're going to bring everything that we know about our functions together, and we're going to look at some applications. And it says actually building functions and mathematical models. Mathematical models are just mathematical situations that apply in the real world. So here, or apply to another given situation. So in example 1, it says to let P, which is a point, and we have an x coordinate and a y value, a y coordinate to describe point P. And that point P is on the graph of y equals x squared minus 1. So if I just think about what that looks like, we should know what that looks like. If this is my function, I know I have a parabola because it is a quadratic function, and my parabola should look something like this. And I am going to pick a point P that can be anywhere on my parabola. And my coordinates for point P are just x, y. And I'm also going to just define here that this is the function y equals x squared minus 1. So here in part A, it's asking us to express the distance from point P to the origin as a function of x. So I want to know, if this is my point P, what is the different distance from P to the origin? All right, so we're going to write this as a function of x, but to start off with, we know that distance is, I'm going to write this a little bit differently, the change in my x values, change in x squared, plus the change in my y values, and that value is squared. So the change in x still means x2 minus x1. This is still y2 minus y1, okay? And we're going to square those values. So if one of my x values is x, because I don't know where that is on the parabola, and my y value is, I'm sorry, the other x coordinate comes from the origin, which is 0, 0. If I look at the change of these x values, I have x minus 0 squared and y minus 0 squared. And that really gives us x minus 0 is just x. So that gives us the square root of x squared plus y squared. Now this is a distance formula, but we want to write this as a function of x. So that means we only want x's in our function. And I know by the description of our function that the y value is x squared minus 1. So I'm going to substitute the y for x squared minus 1. So if I rewrite that, I have x squared, just from the beginning, plus what y equals, which is x squared minus 1, and that value is squared. Now I need to simplify that, so I start with x squared. Now this x minus 1 squared means x minus 1 times x minus 1. Okay, we can't just square the x and square the 1 and say we're done. So if I do FOIL, I do have x squared. Whoops, this is x squared minus 1, and then that's squared. So x squared minus 1 and x squared minus 1. X squared times x squared is x to the fourth. Then I have x squared minus 1, or times negative 1, and negative 1 times x squared. So that gives me 2x squared. So that's negative 2x squared. And then negative 1 times negative 1 is plus 1. And if I simplify this and just kind of rearrange my exponents from descending order, I'm starting with x to the fourth, highest exponent first. I have 1x squared plus negative 2x squared, or 1 minus 2 is minus 1x squared, and then a plus 1. So this is the function as this is the distance to the origin as a function of x. So that means wherever I put my point, if I know the x value, it will give me the distance to the origin. So let's say our x value is 0. So here's part A. Now let's go to part B. If my x value is 0, I'm going to plug in 0 into the function. So I have f of 0, which represents the distance from the point to the origin. So I'm going to plug in 0 for x, and I have 0 to the fourth power plus or minus 0 squared is 0 to the second power plus 1. So this is 0 plus 0 plus 1, so that's the square root of 1, which is 1. So this is saying when x equals 0, here's my point, and the distance to the origin is 1 unit. Let's try part C. Now x has a value of 1. So if x is 1, where is, or what is the distance from that point to the origin? I use this function again, so I have 1 to the fourth power minus 1 squared plus 1. 1 minus 1 plus 1 is the square root of 1, which is 1. So if x equals 1, the distance to the origin is 1 unit. So what if x is something crazy? What if x is the square root of 2 over 2? So the square root of 2 over 2 is going to be somewhere over here. So my x coordinate is the square root of 2 over 2. If I want to know the distance from this point to the origin, I'm going to plug in the square root of 2 over 2 in for x in this function. So I will take the square root of 2 over 2. Now this is to the fourth power. And then I'm going to subtract the square root of 2 over 2. And this is to the second power. And then I'm going to add 1. So when I simplify these, the square root of 2 over 2 times itself 4 times. This would be the square root of 2 times the square root of 2 times the square root of 2 times the square root of 2, which is the square root of 16, which is 4. So I have 4 on top, and 2 to the fourth power is 16. And I'm just going to leave it right like that for right now. We'll simplify even further in a minute. So this is squaring the square root of 2 over 2. If I square the square root of 2, I get 2 over 4. And then I'm going to add 1. So now I need to simplify these. Best way to do that is to get a common denominator. And if I change these all to 16ths, I have 4 over 16 minus 2 4 is the same thing as 1/2. And if 16 is on the bottom, that's the same thing as 8 over 16. And plus 1 is the same as 16 over 16. Okay. Common denominator. So I have 4 minus 8 plus 16 is 12 over 16. Still in the square root here. And if I come down here, I'm running out of room. But if I come down here, I have the square root of 12 over the square root of 16. Bottom is easy. The square root of 16 is 4. And the top value, the square root of 12, is the square root of 4, which is 2 times the square root of 3. Which I can actually simplify a little bit more. I can divide by 2 on each of these, so this is the square root of 3 over 2. That's even more simplified. Right? So that means if this point has an x-coordinate of square root of 2 over 2, then the distance from this point to the origin is the square root of 3 over 2. Woo! That was a long one. And in part E, it asks us to graph the function and find where D has a local minimum. Well, here is a graph of the function, and I've been using that as an aid to help us understand what these mean. But to answer the question, a local minimum, the local minimum is right here. The minimum of this function is -1. And that happens when x is 0. And this would be part D, or part E. Okay, I know that looks a little messy there. Okay, so we were just taking all the parts that we know and kind of putting that all together. In this next one, we have a rectangle, and it has one corner in quadrant 1 on the graph of 25 minus x squared. So if I look at this graph right here, this graph is showing us, here's 25, and minus x squared is a parabola, and it's going downward. If x is 5, 5 squared would give me 0. So here's a x-intercept here. So this is just showing us, I'm drawing half of this parabola here, or a section of it. And here we have a point which is xy on this parabola. We don't know what the coordinates are, and actually I can change the coordinates. And if I were to do that, and by the way, this point here, if I connect the points where it shows us, we are going to have a rectangle, and the shaded area here is the area of that rectangle. So if I were to move this point up here, I would have my area being in this section right here, and we're going to actually calculate what the area is at different points of this parabola. If one of the coordinates is here, my area would be in this section here. I can move my point down here, and my area would be in this part right here. So first they ask us to express the area of the rectangle as a function of x. So I know that the area of a rectangle is base times height, right? Base times height. But in terms of our graph, our base is going to be an x value, and our height is going to be a y value. So we're going to change this to x times y. Now, since we're writing the area as a function of x, I am going to say that the area of this rectangle is our base, which is x, and our height, which is y, but y actually equals 25 minus x squared. 25 minus x squared. Or I can say, if I get rid of the parentheses, this is 25x minus x to the third power. So my area as a function of x of the triangle is 25x minus x to the third power. Now the domain of this area is going to be what x values can we have in here. Now I can't have a negative x value, so I know that my x value is going to have to be greater than 0. So for my domain, I know x is greater than 0, and it has to be smaller than 5. Because if my x value is 6, that's not going to work. It's not going to be inside my parabola. So, and x has to be less than 5. And I can write this in the set notation, which is using parentheses because it is not equal to. So this just represents that my domain has x values between 0 and 5, but not equal to 0 and 5. Then it says to graph the area function. Now on this part, I'm going to use Desmos. Now if I were to graph the area function on Desmos, it's going to look like this. Here is a minimum value, so it's going to come down like this. Then it's going to come up, go through the origin, and it's going to hit some maximum value up here, and then come back down. And this is the 0.5, this is the point -5. So this is what my graph on Desmos would look like. And it's asking us to find the largest value. So the largest value is up here, and this would be the largest area value. So if I touched on that point is going to be the point 2.887, and the y value is 48.113. Now the largest value, or the maximum, is the maximum area, which is 48.113. And I should say area here. The max area is 48.113 when x equals 2.887. Okay, the highest area would be at the maximum. Okay, so on the next page, we actually are going to skip this for a couple reasons. There's some really messy things here. It's not very clear. We're going to substitute this with a value or with a specific problem that we're going to do in class instead. So skip this side. You can exit off in your workbook. So we're just going to stick basically with these two examples here. All right, so that is all for Unit 2.